All right, let's go ahead and get started. Any questions about anything before we get going? So I should let you know about some stuff coming up. I think for the section we went over last time, that integration with tables was pretty short. There's one more thing I got to show you, but I think the next two web works are due like in the next 4 days or so, right? I think one of them's due Sunday, and the next one's due Tuesday. And I think the written homework is due just a couple days after that. So just a reminder, my office hours just started this week. So Tuesday from 2 to 4, Wednesday from 10:30 to 11:30 in room 303 upstairs. If I'm not there, anybody else can help you, or if you'd rather talk to me, then we can set up an appointment some other time. Also, the first test is the 18th. So just a little bit less than 2 weeks. So a lot of big things coming up. If you'd like to talk, let's do so. Otherwise, there's one last thing I want to talk about with this integration by tables, because it is important for the written homework. It is, using those tables in the back of the book, or I posted a document on Canvas where basically I just copy and paste all those in there. But knowing how to use like online calculators to do integrals, because there are some that work pretty well. So there are a lot. The one I prefer, just because I don't know, I'm most comfortable with it, is on Wolfram Alpha. Has anyone ever used anything that these people make? So you have? Okay. So they do a few things, and one of them is they basically have this program that can compute an indefinite integral, which is something that most of the TIA calculators can't even do. So I at least want to show you how this works. So when I say it works pretty well, so let's look at one of the functions we integrated with tables last time. So this cosine x over sine squared x plus minus 9. So we found this thing involving natural logs and sines. If you look at what their indefinite integral looks like, can you all see that? Obviously it looks very different. So I don't know how often you all use the hyperbolic tangent function or its inverse. This is maybe the first time you're ever hearing of it. So that's what I say. Like that's the only complaint I really have about it, is that it might throw an integral back to you in a form that you don't even recognize. So you could easily Google what that hyperbolic inverse hyperbolic tangent function, like other formulas for it. But let's look at one that I think came back a little more realistic, or a little more similar to what we wanted. So I'm gonna delete this. It's a little bit like web work, where it's kind of sensitive into how you type things in, but if you got the hang of that, you can get the hang of this. So I think this is the function we just did, or that. So that looks identical, or not identical, but equivalent to the one that we integrated last time, right? So this integral that it gives back, clearly it's not identical to what we came up with, but is it equivalent? Yeah. So I think the biggest difference I see is that if you would have taken the one we came up with here in the black ink and factored out the half, I think that's the only real difference, right? And they move the terms around. So I bring this up for a couple of reasons. First, I do ask you to do this on the written homework to verify things that you found by hand. But also you can always use this thing to kind of verify that you're on the right track. I don't promise it'll give you an integral back that is in a form that you will recognize immediately, but it will give you something correct back. Any questions? Go ahead.
Will we get to those hyperbolic functions in this class?
No, I have very little experience with them. I mean, I've taken math classes in a lot of different areas. I've very rarely ever. So I've used the hyperbolic sine and cosine a little bit. I've never touched the hyperbolic tangent function. This is the first, like me going through this example and throwing it into Wolfram is the first time I've seen it. So they have applications. I don't really know what they are. Is this something you think you can find, or should I drop a link in Canvas somewhere? Okay. If anybody has trouble, let me know. I think really probably in my online integral. Yeah, I think this is the one I always search for. So Symbol Lab is another one that works well. I think Wolfram was probably the first one that existed, so it's the one that I've been using the longest, so I just keep using it. But I've used the Symbol Lab one before, and it works pretty well as well. But yeah, give that a shot. I mean, I think even outside of the things I'm asking you to do on the homework with it, it's if you're stuck or if you just need a sanity check on something, you want to figure out like where that negative sign is that you flipped. It's a good thing to it's a good resource if you're in a jam. Any questions about that? All right, so let's move on. So section 6.5 is the one we're going to start now. And this is going to be the last one that is covered on the test that happens on the 18th. So we'll probably get into some other stuff before the test happens, but just know that, yeah, 5.5 to 6.5 is the scope of that first test. Come on. Go away. Okay. All right. So a lot of all the integrals we've found so far have been exact, or I mean approximated, but basically we have had the means to find them exactly, but we don't always have the means to do that. So if you think back to the way you talked about integrals at the very end of Calc 1, probably the quintessential example you talked about is how to find the area under a curve. How did you talk about approximating that area under a curve? Okay, was there any kind of like approaches you had? Go ahead.
The Riemann.
Yeah, what is a Riemann sum?
Dividing it into different subsections and then finding the area of each of the subsections.
Okay. When you talk about Riemann sum specifically, Riemann only divided, he was very specific about the way you ought to divide up this area. So what was the big restriction he has? So, for example, if I want to divide this up into shapes, like this is like vaguely triangular. Yeah, so, okay. So that's one of those, it's hard for me I feel like you knew what I was looking for, but I didn't know how to ask you the right way. But that's something that Riemann dictates, right? Is that when I split this up into subintervals, pretend I can draw straight lines. These have to be rectangular, right? That's not even close. But that's kind of the main thrust of a Riemann sum. Are there other ways that you talked about previously about how to break these things down? Go ahead. So yeah, I mean, if you want to get away from rectangles, you can, I mean, for this kind of curve, I think I can more faithfully recreate the curve if I can draw trapezoids along it. Any others you've talked about? But these all kind of have the same motivation, is that there is no canned geometrical formula that gives you the area of whatever this shape is. So if you can approximate it with a sum of simpler shapes that you can find the areas of, that'll at least give you an estimate. So a lot of ways to do this. When you're talking about Riemann sums, you probably talk about left-hand endpoints and right-hand endpoints. And that's just all about like, if you're going to define a rectangle, that means you're taking a subinterval of that function. So any one of these like blue intervals here, And since you only could have a horizontal line for that part of the function, you're basically saying that you're going to choose one height to represent the entire, basically all the y values of the function in this vicinity, right? So left endpoints, one way to do that. Right endpoints, you can really choose anything in there. You can choose the highest point, lowest point, but as long as you make a choice in there. Midpoints as well. Trapezoid we talked about. So let's talk about this integral. So don't necessarily know what this curve looks like. I also think we could find this integral exactly, right? But let's kind of use a few different schemes to estimate what this looks like. So I want to use a Riemann sum, specifically a left Riemann sum. So after I divide this thing up into intervals, like subintervals, I am going to take the I'm going to take the left endpoint of each interval to represent my y value for the entire subinterval. So any questions on the motivation so far? So if I want to use four subintervals over this larger interval, where are those boundary lines going to be? 0 to 2 is kind of that's the larger interval, right? The full interval I'm trying to integrate on. So I want to split this thing into 4 intervals. Go ahead.
You need 2 minus 0 over 4.
2 minus 0 over 4 is going to give me what?
Would you ask me? This is minus 7.
Basically, I'm asking like, yeah, where are the bounds? So 0 to 2 is the large interval,
They'll give you how long 7 is.
right? So if I want to, I want to divide those things into, and that's another restriction that Riemann had for Riemann sums, that if you're going to divide up an interval, it has to be done into equal width pieces. So in this case, if I don't want to divide it into 4 pieces, I want to divide it I want to let my x change by a half every time, right? All right, so now that I have my x-axis kind of partitioned, what else do I need to do to start finding this Riemann sum? What x values am I going to need to pull from? I have 5, right?
0 through 1.5.
0 through 1.5. Why am I ignoring 2?
Because you're doing a left Riemann sum.
I'm doing the left Riemann sum. So let's draw some dashed lines in here. These are my boundaries of my x value, right? So I'm going to I have 4 subintervals, but I have 5 basically boundary points. But yeah, in this case, I only care about 4 of them. So let's make a table to capture that. What x values do I want? What y values do I want? I want 0, 0.5, 1, 1.5. When x is 0, what is y? 0. Okay. So first, let's put the points, and then we'll draw in the rectangles and the rest of the curve. If x is a half, what do I get? 1 over 1.25. Is that 0.8? I think. Okay. If x equals 1, y equals 1. And if x equals a half, that's 3 over. Somebody give me a hand with this. We're approximating, so calculators are fair game. 1 plus 9 over 4. Somebody bail me out, so I have to keep thinking about this.
12/13.
12/13? No, we go out in decimals.
0.92.
Sounds great. Okay, so, and for good measure, let's get what happens when I plug in 2? That should be easier for me to do in my head. 4/5. Okay. So this doesn't go any higher than 1. So let's draw a real quick sketch to get our bearings. So 0, 0. Come on. 0.5, 0.8. 1, 1. So the curve looks something like this, right? I mean, maybe we probably need more points to get a better idea, but that's our curve, right? And the way we're going to find the area is by finding the area of these 4 rectangles. So that'll give us an estimate, but how good do we think that estimate is going to be? I mean, I have one real concern that we're going to get. What are we going to get for the area on that first subinterval? We're going to get a 0, right? So let's talk about that now. How do we find the areas of a rectangle? Length times width, right? So what is the length of each one of these intervals? 0.5. And how do we get that 0.5 again? Right, so equal subintervals. So I think I even heard somebody say it before. Delta x is basically the change in x. How big is the full interval? It was 2. So the way I get that in general is to subtract the basically the difference between my least bound and my greatest bound. And I divide that over the number of intervals I have. So my area is going to be that delta x times. Actually, let's look at this first. The area is going to be equal to area 1 plus area 2 plus area 3 plus area 4. So the first area is going to be delta x times f of what value? F of 0, right? Plus delta x times f of 0.5 plus delta x times f of 1 plus delta x times f of 1.5. Do we agree that we can factor out that delta x? So this should be so any questions so far in the setup, any part of this? So how we find where our boundary points are, our boundary x values, how we found the corresponding y values, how we've set up this integral, this approximate integral we're trying to set up. Anything at all? Go ahead. What's what? Delta x. Delta x is the dx. Are you talking about this dx here?
No, the one that you were calling by delta.
Yeah. Right.
Okay, I thought it said AX.
Oh, yeah, no, sorry.
Yeah.
That's a delta. So I think it's delta. All right. Are we ready to find this area? So 0.5 times the sum of 0 plus 0.8 plus 1 plus 0.92. All right, you're on. What does that come out to be approximately? $1.362. We agree with that number? Sounds reasonable. How we doing? Okay, go ahead.
How do we use like the sums or anything like action?
So in general, yeah, so you're right, and I might have said this before you got here, but for this one, we have the tools to integrate this specific function. So I'm not sure if this came up when you're all taking Calc 1, but basically we know that if a function is continuous, it has an integral. But that doesn't mean that we know the integral exists. There are several functions we don't know what that integral is. We don't have like good ways to get them. So the reason I chose this function is because at the end, we're going to find the exact value and see if our approximations are any good. But there are plenty of functions that, you know, the kind of the quintessential one that you've probably seen before is this. So e to the x squared is a function that we can find that derivative, and you've probably found that derivative before. The integral is something that we know what it is, but it's complex looking. It involves something called the error function, which is a little more involved than anything we want to touch in this class. So all that to say that every continuous function has an integral. E to the x squared is continuous. But it doesn't mean we know what the function is. We have a lot of things like that in math that we have proven that certain things exist, but we can't prove that we can find them. For example, we know that there's an infinite amount of prime numbers, but right now we have a largest known one, and we have failed to find things that are bigger than it. But we know they're out there. So we did left Riemann sums, right? Now I want to do right Riemann sums. So we're keeping the function, we're keeping the interval 0 to 2. We're keeping 4 intervals, so those 3 things are going to stay the same. So what things have to change for us to find this area?
We ignore the 0.
We ignore the 0. Okay, so we had this table of values that I wish I could copy and paste, but I'll just put the skeleton back. So the 5 points we found were 0, 0.5, 1, 1.5, and 2, right? So in the last example, we ignored what was going on at x equals 2, right? So now Saul would like to ignore what's happening at x equals 0. Does that sound right? Okay. So then how am I going to find my area this time? So I still need to find an area that's built up of the sum of the area of 4 rectangles. But now how do I find, like, what 4 rectangles am I trying to find the area of? So I want those 4 values starting at 0.5. So for area 1, I'm going to multiply 0.5 times f of 0.5, right? How do I find area 2?
0.5 times.
Okay. Why did we change the 0. Why did we keep one of the 0.5s and change the other one?
That's the value of my value times the x value stays the same.
Right. So that's one thing I want to point out, because this is something I see quite a lot, is that basically changing that delta x and the x value I'm looking at. So remember, the way that Riemann defined these sums that have his name is that all my areas need to be rectangular and they all need to have the same base width. So moving on, area 3 will be same width, new height, and area 4 will be same width, and then the far right end. What were these values? What was the f of 0.5? 0.8. So really, a lot of these should be, I mean, three of these areas should be identical to three of the ones that we did last time, right? Mostly going off of memory, but I think those are the right numbers. Good, okay. So if we add those all up, what do we get?
1.76.
What's that?
1.76.
1.76. I think that's quite a bit larger than what we got for the left sums. Yeah. So now that we've done a couple of these, questions about what we kept, like what did we maintain from the first example? What did we change? Do we understand why we changed those things or kept them fixed? All right. Now midpoints. Now what do we got to do? Can we use anything we took from our first two examples? What's that? The delta X we can use again. Why do we get to use that again? Why do we get to, so
Still the same when on all the.
so it's same larger intervals here in two, and I'm still dividing it up into the same number of subintervals. So yes, delta X is still equal to 0.5. Anything else we're going to keep constant? So it sounds like we're changing a lot. So someone give me a change that we have to make to find the value of this sum. What's that? What's 0.25?
One of the points here.
Okay, so I think the first one we have to take, I'll call it x1 equals 0.25. Where's the next one going to be? 0.75. So the delta X not only tells you how big your subintervals are, it should also tell you the even, like the consistent spacing between your sample points, right? Do we agree that those are my 4 sample points? Okay. So I'm trying to go ahead, Saul.
So if we were asked to find the midpoint, just the midpoint without doing the left and right prior, how would we
Yeah.
find those points first?
How would you find what points? I'm sorry.
Those points first.
That's a good question. So I haven't drawn a graph in the last example, but I'm not going to graph the curve again. But one thing I think is a wise thing to do is to either through a picture or by doing it algebraically. In fact, I'll do it both ways to kind of show you multiple ways to think about it. But I know my larger interval is 0, 2, right? How many subintervals do I need? 4. So that tells me where the intervals begin and end, right? So from that information, from knowing what the interval is 0 to 2 and knowing how many subintervals I want to make. So in the notation your book typically uses, I mean, in general, like when they're trying to generalize these things and put formulas around them, A and B usually stand for the lower and upper bound of the integral, and N stands for how many rectangles you're going to divide it up into. Or I shouldn't say rectangles. They're not always going to be rectangular. And then we also have that delta X is equal to how wide the whole interval is divided by not generally N. And then how many pieces I want to split that up into. So to answer Saul's question, I think one way that I would figure this out is by getting my bearings with a picture. If I know that one of my sub intervals I'm going to look at goes from 0 to 0.5, how would I find the midpoint between those two things? Add them up, divide by 2, take the average. And I think we should get the 4 points that we've already identified. Could I also do this without drawing a picture? So I know that A is my left endpoint 0. I know that my delta X is, in my case, 1/2. So if delta X is 0.5, that means my first, how do I find the midpoint of my first interval? That's going to come from, well, where's the left end? The left end is always going to be A, right? And then I'm going to add how many delta X's to that to get to the actual sample point I want. Let me be more clear. So in our case, our subintervals are 0.5 units wide, right? So if I want to find the midpoint, how far from the left side of the interval do I need to go? Half of whatever a dx is. So if I'm doing midpoints, you know, my first sample value of X is going to be, you know, the left end of the entire interval, in this case 0, and I'm going to add half of a delta X to that. So if that's true, how would I find the next place? Where's X2 going to be? You can add a delta X to what? Right. You can just add a delta X to X1. And then where would X3 be? You can add a delta X to X2, or you can add 2 delta X's to X1. So take advantage of the fact that, you know, Riemann defined all these things for regular, consistent, predictable behaviors. So any questions about how to find these midpoints, or at least where the X values are? Can we find the area now? Okay. So still the sum of 4 things. How would I find the area of that first rectangle? What is the X? What's the base? The base is still delta X, right? So 0.5 times, in fact, 0.5 times what? So f of, yeah, 0.5 times f of 0.25. And so on. Does someone have numbers for me?
The first one is 0.47,
0.47.
then 0.96.
Yeah, I'm gonna do some mathematical cheating. Hold on. All right, 0.47, and then
0.96,
cool.
0.98, and 0.86.
All right. And finally, what's up? Do I have a final result for all that?
1.63.
1.634?
5.
5. Okay, so that's a lot of Riemann sums. We got 3 different areas, all using the Riemann scheme, right? Any question about how, like, the differences between the commonalities between? Go ahead.
Out of all 3, which one would be considered to be the most accurate?
I have no idea yet. So here's the thing. For this specific one, I could probably figure out which one's the most accurate. In general, there is not one that is. I mean, all functions behave differently. You can't really ever say that one is generally more useful or more accurate than the other. In fact, what's the only way to make this more accurate?
Add more points.
Yeah, you just need more rectangles.
We can do that infinitely, right?
You can't. If I'm asking you to do it by hand, no, but yes, in general, you can get a sense for what that limit's going to look like as you have an infinite number of rectangles whose width is approaching 0. That's what an integral is, and that's probably the way that, if you don't remember, that's probably the way you saw integrals being developed. Is first you're going to chop this up into rectangles. Now imagine what happens if those rectangles get infinitely thin, and I have infinitely thin. That's basically what an integral is. How are we feeling? So let's move away from rectangles and use trapezoids. Is a trapezoid just a thing you know how to take an area of? One more time, sorry.
Space 2 times divided by 2.
Okay. So the area of a trapezoid is equal to 1/2 times base 1. One more time, I'm sorry. I want to write it exactly how you said it.
Base 1 plus base 2 times height divided by 2.
Is this a formula we've seen? If we haven't seen it, does it make sense now? Okay, so let's hold on to that. Let's try to redraw this thing. So let's write down our points. Is it okay to go back to our 0, 0.5, just every half? Maybe you don't know because I'm not telling you how we're going to define these trapezoids. So I'm using my memory, so help me out if I go astray. So those are my values at my boundaries, unless someone corrects me. So my curve looks something like that, right? So how do I draw a trapezoid that covers the first interval? I'm going to draw a straight line that connects the endpoints of the interval and a vertical line that completes the trapezoid. Trapezoid. You look like you have a question. It is a triangle. So this is the trapezoid method, but it's not always guaranteed to give you a trapezoid because sometimes one of the heights is 0. That's what we have in this case, right? This will be more clear, hopefully. So basically, I'm going to do the same exact method. Connect the endpoints of the subinterval with a straight line. Draw a vertical line down. Vertical? Is good enough good enough? So area 1, area 2. That's a trapezoid, right? And I'll continue. So now I have 4 areas. I don't promise they're all trapezoids, but we can treat them all like they're trapezoids. So have people seen this formula for the area of a trapezoid before? Do we know why it works? Basically, what you're doing is you're kind of transforming a trapezoid into a rectangle. And the way you do that is by finding, so a trapezoid has a height, according to that formula. It has two different base lengths, but if I average them together, then I can kind of treat the thing as a rectangle. Go ahead.
Is it almost like we're cutting off the part of the rectangle that would be on the side of the curve?
Cutting off the part of the rectangle.
I mean,
You're cutting off part of it, but so here's what I say when you're modeling these things as rectangles. So let's take area 2 here. I'm going to draw a rectangle that I think has the same area as area 2. It's going to go through the midpoint of this straight line. So you can kind of think of the trapezoid rule as kind of like it's like the midpoint rule, except I'm not taking the midpoint of the x values now. I'm taking the midpoint of the y values and then treating that thing as a rectangle, which is just a different way to look at what a trapezoid is. How are we doing so far?
So you still treat the triangle as a trapezoid?
You can. So, I mean, let's use this weird formula on it. And by the way, this is the formula that I think you probably all saw in geometry a while ago. Our trapezoids don't really have different base lengths. They have different heights. We're kind of tilted them on their sides, right? So I'll just rename. Like, do we all agree this is the same formula? I'm just looking at a trapezoid tilted onto its edge. But yeah, you can. So what happens if I treat that area, that triangle, as a trapezoid? Area 1 equals height 1 plus height 2, so 0 plus 0.5 over 2 times the height, which is, or no, times the base, which is 0.5. How do you find the area of a triangle? So it's 1/2 base times height, right? So essentially, you can think of a triangle being a trapezoid that has no height or no base length on like one of those sides.
Because one in the bracket must be 0.8.
Yes, thank you. So that's a good reason to write this in general before I start making it really specific. So our area 1 is going to basically be our f of 0 plus f of 0.5. So those are my heights, right? I average those heights, and then I multiply it by delta x, which in our case is going to be specifically 0 plus 0.8 over 2 times 0.5. Thank you for the catch. We happy with that calculation? We have a number for it? No,
What did you say the answer?
I don't think we have one yet. Point 0.2. Yeah. So area 1 is 0.2. Let's write out long form, just one more of these. If I want to find the second area for the trapezoid, what points am I going to use? F of 0.5, f of 1, all over 2 times delta x. So 0.8 plus 1 over 2 times 0.5, which is I believe 0.45. All right, let's go a little quicker. So area 3 will be 1 plus 0.92 over 2 times 0.5, which someone's going to give me a value for, because I don't trust myself on either one of these last two. Okay, maybe I should trust myself. $1.72 divided by 2 is 0.86. Somebody please check that last one. Okay, cool. All right. Then if my final area is equal to my sum of my areas, what does that come out to be? $1.56. Do we think this is, so in general, do we think trapezoids are better or worse than using rectangles to help us? Go ahead.
I think it's better because it helps us calculate the area much more accurately. There's not much jumps outside or much white space left inside.
Right. So one thing the trapezoid scheme does that the rectangles don't is that, you know, for these Riemann sums, and Riemann didn't really develop Riemann sums to be accurate. I think it's just quick and kind of simple to conceive of. How many y values are dictating your height for your rectangle when you do a Riemann sum? It's just one, right? It's basically, for the ones we did, we chose either the left end of the interval, the right end of the interval, or the exact middle of it. But for trapezoids, we take a subinterval and both of the y values have something to do with what that area is going to be. So intuitively speaking, hopefully it is more accurate. And when we get that exact value next time, hopefully 1.56 will be close to it. I don't think I want to start Simpson's rule before we go. Yeah. It's kind of a weird thing. I don't want to get into it in 90 seconds. Any questions about what we've done so far? Or about anything else that's going on in the class? All right. Have a good weekend. I will see you all Monday. Yeah, 1 second.